Hello.
Yes.
Yeah. So I can see some of you are here already. So, so how was your week? Did you guys use the break to to catch up with this course, or was it just a holiday where you forgot about this course completely? So, so, uh, so any questions so far? Have you done the? Have you done your? Have you read the stuff that you are supposed to read?
Sir, regarding the assignments, I have some questions.
Yeah. Go ahead.
So, question 3 and the proof for Kruskal's algorithm are basically the same.
What was question 3? I forgot.
Question 3 is if there are distinct edge weights, then the MCST is unique.
Yeah, basically, you're right.
So, like, should we repeat it?
No, it's okay. I mean, if you have that, yeah, it's okay.
And for question 5,
Hmm.
so the algorithm I'm using, it's recursion based.
Now, what was question 5? You remind me.
Question 5 is a number of paths from source to destination in a DAG.
Right. Okay.
So I think calculating complexity is almost impossible because I'm calculating complexity for a single vertex multiple times.
Okay. I mean, see, it's nothing. Nothing is like impossible, right? So I mean, like you have to give me some upper bound, right?
So like I can find a bad upper bound, but it's bad.
I mean, if your algorithm is not good, then it will be, mm, it will be high, right?
I
But
mean,
but at,
see if I
but
can,
again, at the same time, you should realize that the total number of paths that can be there, okay, can actually be quite a lot. Okay, how many number of paths can there be from U to V? Hello, how many number of minimum paths there can be? So that number itself is not small.
sir, I mean, we haven't studied memorization yet, but like if I can do that, then I have a OE algorithm.
Okay, that's good. OE algorithm is pretty good. I mean,
No,
that's,
we haven't done memorization yet. So
I mean, you have not done what?
memorization, like storing the functional values without calculating it again and again.
Uh, I mean, if you can do it, you can do it. I mean, there is no problem with that. If you have,
Okay, sir.
okay, because anyways, whatever the stuffs are there, people can find it out by themselves also. None of them is complicated. Okay, yeah, you are saying that you should not be calculating the same value multiple times.
Yes, sir.
Yeah, so that is the, of course, that is a very natural thing that one should consider. How can you save by not doing this same computation again and again?
So
Yeah,
then the algorithm is just OE. That's fine.
yeah. So I mean, I got a couple of people who kind of wrote to me about the union find algorithm and how can you have the Kruskal's algorithm without the union find and algorithm and all those things. But here I want to, I think I told about it earlier also, but here also I'm saying. So what does Kruskal's algorithm do? Kruskal's algorithm tries to find the minimum spanning tree by using a somewhat of a greedy algorithm, right? It basically picks the minimum weight edge such that no cycle is produced among the set of edges that has been picked up, right? And it keeps on doing it till at some point of time it finds out that you have exhausted all the edges. Now that is the Kruskal's algorithm. Now the Kruskal's algorithm has two important parts. Okay, the first part is actually that why is Kruskal's algorithm correct? And this is something that I believe was done in your discrete math course. So this is the case when, I mean, you are doing a very localized stuff, right? At every point of time, you are trying to find out the minimum edge weight such that it doesn't produce a cycle. And at the end of the day, we want to claim that whatever we are producing is a minimum spanning tree. Minimum spanning tree is something which is a very global property. So why is that the case? So that proof you have to write. Okay, that proof you have to be convinced about. It's a formal proof using in graph theory that you have to do. That whatever happens, the Kruskal's algorithm always will output an MST. By the way, you should be a bit careful over here. It's not that every MST, okay, can be produced by a Kruskal's algorithm. Okay, that is not necessarily the case. Okay, so there might be MSTs that are not produced by a Kruskal's algorithm, particularly if the Kruskal's algorithm is selecting these edges in a particular way, a particular order. I mean, if there are ties and so on. But irrespective of that, it will always output something that is a MST. The main idea is that a graph can have multiple MSTs and will output one of them. So this part is very much something that is very discrete math-like rather than algorithmic, and that's it. Now the second thing is that what is the time complexity of the algorithm? Now the time complexity of the algorithm is kind of also pretty simple, right? What do? You first of all order the edges. So that takes order E log E, number of edges, according to the weight of the edges. And then you keep on taking the minimum edge weight, minimum weighted edge, and check if you put that one in your selected edges, will it create a cycle or not? Now whether a cycle is being created or not, that can be easily be checked using a DFS or BFS, right? That's not a problem. But that will mean that every round, every time you take an edge, you put it in and check whether that is producing a cycle or not, you are incurring an order E plus V plus E number of edges, right? So, I mean, so a normal, maybe let me share my screen. Can you see my screen?
Yes, sir.
Yes.
Yeah. So basically, if you have the normal, so you have order E log E is for the sorting of the edges. By the way, I am not repeating the Kruskal's algorithm. If anybody is there who has not yet gone back and revisited the Kruskal's algorithm, then I think it will be pretty tough for that person to follow this, whatever I'm saying. But that is something that you are supposed to do. So order E plus is sorting the edges. Now for each round, each edge, right? You can check, you have to check if a cycle is formed. Now this question is how much time will this take? What is the time complexity for this? What is the time complexity for this? Now a bad one is using a BFS or a DFS, and that is order V plus E, which would mean that the runtime of the algorithm, runtime of Kruskal's, will be order, actually V plus E is basically order E times E is basically order E square times, right? I mean, E times order V plus E plus E log E, which is order E square. Now question is that can you get better than this E square? Okay. Now the main idea is that all you have to do is that whether this cycle is formed. Now BFS and DFS does a way more job than just finding a cycle, right? Can you use that? Right. So in other words, say I have a graph like this, right? Some graph like this. Now at some point of time, I have chosen some edges. So this is an edge I have chosen. I have also chosen this edge. Now I want to check if by selecting, say, this edge, will I create a cycle or not? How can you do it? Other than BFS and DFS? When will a cycle be formed? Note that a very crucial thing that you do here is that at no point of time in the Kruskal's algorithm are you creating a cycle in the blue edges. So that means the blue edges forms a forest, a collection of trees. Right? Blue edges always forms a collection of trees. And in a collection of trees or in a tree, when can a cycle be formed? Or when in a forest, if I add an edge in a forest, when can a cycle be formed?
If
If
both
both
the
the endpoints are in the same tree.
Exactly, right? So all I have to check is that is the both these endpoints, in this case this and this, are in the same tree. Or in other words, I need to check if both of them are in the same connected components. Right? And that is exactly what we have to do. We have to somehow keep track of the connected components. Right. So in some sense, I have done this one. Okay, I have find out that this edge is not, this is not in the, it doesn't create a cycle. I draw that. Fine. Now, I might want to ask you, what about this edge? Now I figure out that, oh, see, this edge is again not producing a cycle, right? Which means that I can take this edge and take it inside my selected edge. But note that what has happened. Till that time, my connected component was this and this, right? But once I take this edge over here, my connected component I should kind of, I should merge these connected components and to create a bigger connected component, right? So in some sense, what I need is, the connected components are nothing but a partition of sets. Partition of sets. Now in this case, this is a set E. Sorry, set V. Right? Partition of the vertex sets. And what all things do you have to do? Basically, I have to do two things. Number one, merge two sets, right? If I get, merge two sets in the partition, right? So I have a partition of sets, meaning say I have this set and I have this partition, and I can ask you that, oh, can you merge this set and this set? What basically I would like is basically for you to, remove this intermediate part and kind of create a bigger set out of here. Okay, so this is the important thing that you are expected to do, right? You have to merge these two sets. Connected components can become larger and all. And the second most important thing is check for, so I will give you an edge, right? Vertex, like say I give you this vertex and I ask you, oh, is this vertex in this component or not? Right? I have to ask that question, right? I have to get the answer about which partition is a particular element belongs. So check for which check which set an element belongs. So these are the two important steps that I need to do. That's all. I don't want to do something complicated. I don't want to find a cycle or something. Right? I want to just, if you can somehow give me a strategy in which I can store the partition, I can store a partition of these sets. Now, what is the initial partition? Initial partition is, of course, all the vertices are in different partitions, right? Different sets. So all the connected components are individual. And then when I go on, I will basically be using the second thing to check if I add an edge, will I create a cycle or not? Or in other words, whether the two end points are in the same partition or not. And if not, I will kind of select this edge. And in that case, I have to merge those two sets. The connected component should kind of collapse. So is it clear that this is the two things that we want?
Yes, sir.
Did I go fast for anybody? Everybody is fine with this, whatever I told? Okay. So here comes the point, okay? Here we need, so DFS and BFS does that, but you can see that all we are saying is that, is there a nice and clever way of storing the partition in such a way that I can answer these two things? And again, coming back to what we had done in the case of arrays or linked list or heaps, right? So here I want to store my data in such a way that I can answer these two questions, okay? And this becomes a part of our data structure, okay? So there are data structures that help you in doing so, okay? And so I will not be doing this thing right now. Later on in the class, I might want to do that. But for here, what I can say is that if you guys want, you can go ahead and feel and read it. It's a bit complicated, this particular data structure. This is called the union find data structure. Okay. Basically, I mean, you can see why is it called union find, right? Because you are doing two things. You are doing the union of sets and a find operation, right? The two operations that you basically want to do. And this one has so in data structures, see, in data structure, it is very hard to kind of say the worst case time complexity. Okay, this is something that's also another very interesting thing of data structure. So say I want to check a find, okay? I have given a data structure on n elements, and I have asked you to check a find thing. So this is a find, okay? This is a find operation, and this is a union. Okay. Now, as you can see that if the elements are all individual and all those things, right? I might take some time, or I might do it quickly, right? Because they're all single element. I can quickly check things. But if the partitions becomes bigger and bigger, then this find operation might be a bit costly. Because I have a set which has 100 different elements, and I ask you one element and check that, okay, can you give me the name of this Sorry. So there are a lot of these kind of stuffs, right? There are find operations that you can do, right? But so in the worst case, the find operation might take a lot of time. Okay, might take say order n number of times. So that's not very good. So that means if I give you n elements and I ask you to find whether a particular element is in which set, in the worst case, the algorithm might take order n steps. But the important thing is that if I ask the find operation when the elements are single individual elements, right, then I can do it quickly. If not, so this is the worst case, but this can only happen. So the worst case can only happen if the find is after n unions. So maybe the worst case does happen, but that happens, the worst case can only happen if you have done first n different unions, and only then if you've done a find, only then the worst case will be order n. So such kind, in this case, if somebody says that, okay, see, to do a union, I need an order 1 operation. To do find, I in general need order n operations. But this worst case can happen only after so order k operations. But the worst case can happen only after you have done some k different unions. So on an average, the total number of steps that is been required is low. Okay, so on average, now this on average is slightly different from the average that we were doing for the case of sorting. Okay, this is because we have two different operations that we are looking at, and it doesn't make sense to use worst case for both of them. Okay, one worst case can only happen after you have followed up some amount of things.
Sir, you are not audible.
Oh, I was not audible? Oh, for how much time? Hello? Am I audible? Hello? Hello? Hello?
Yes.
Oh, what was the last thing that you heard?
You were explaining the worst case.
I was explaining the worst case.
Like in worst case, you'll have, in average case, you'll have okay.
Okay.
So,
Okay. So good. So let me say in this following way. Okay. Say I give you boxes. Okay, and I have asked you to store the boxes. Okay, I have given you. I will keep on giving you boxes, and you will be storing these boxes in some way. So there are two parts, right? And so you will be storing the boxes in a straight line, in one on top of the other. Okay, and so one of them will be stored. Stored operation is, I think, I will give you a box, and your goal is to put it on top of the pile. Okay, and then the other one is called find. Okay, which is basically, I will say that, oh, can you check for whether there is a box with this label, and you have to find it. Okay, so is this kind of game clear? This is a game that we are playing. Okay, I will keep on giving you boxes, and your job is to put this box on top of each other, one after another, and that is called a store. Okay, and I might ask you at some point of time, oh, find, and when I say find, you have to go and find this whole thing, right? And say I will ask you find only once. So in this case, what can happen is that,
Sir, can you please explain the find thing? What we will find?
so these boxes are a label, right? The A, B, C, D kind of stuff like that. At some point in time, I will ask you for a find a box with label, label, say A or something, some label that I will specify. Okay, so you have to go down this box, pile of boxes, and go and find that box with label A.
Okay.
Okay, so now it is kind of obvious that I will give you a box and you can put it on top of it, and that only takes order one step, right? No complication. Now the find takes order n steps, because that the label A might be the last one, and you have to kind of, it's a stack kind of stuff. You have to go and remove this all the top ones and then find out the order A, right? So in some sense, the worst case runtime of find is order n. The worst case runtime of store is order 1. But the important thing is that this order n, if your find operation takes order n steps, that means that it must have preceded with n different store operations, right? So it must be that I have stored something, and I have made n different store operations, and then I have asked you to find something. So in that case, this find operation takes order n steps. The store operations takes n times order 1 step, and on average, the total number of steps that are taken is basically order n by n, which is order 1, right? So although the last step was costlier than anything, but I can kind of make people, I mean, I can say that for every stored operation, I will charge something. Okay, or I can distribute the cost of finding of this find operation among these stored things. So this is called the amortized cost. I mean, I don't really want to go too much into details of this thing, but that will kind of derail this course completely at this point. But I'm saying it because people, many of you possibly are looking at various things on this union find and all, and you are getting to hear this term, amortized and all. The amortized is basically you have a data structure in which you want to have multiple operations. Okay, so here I have just 2 operations, but you can have multiple operations. And the worst case of one of them, or worst case of them, might be very much higher. But the worst case cannot happen just like that. It can only happen in a special setting. And in that setting, we can kind of say that, oh, we can distribute our, I mean, the average cost is lower. And that's called amortized cost. Okay. So using the union find is exactly one of those data structures. In union find, there exists, so here is the union find thing. And there they say that you can do, if you have n different operations, n operations, meaning n union or find operations, then the amortized cost, meaning the total cost in some sense you can think of, okay, in the worst case, total cost in the worst case is actually something much better than order n square or something. It is something called n log star n. Okay. So, okay, I have not told you what log star is, but I will explain that very soon. Okay, but what it means that if I go back here, okay, that means that I can check instead of this BFS and DFS, okay, that I had to do every time. I had no option but to reuse the BFS and DFS in some nice way. Instead of that, you can use this union find data structure such that after you have done the E number of steps, okay, after the complete E number of rounds, the total cost will be, so maybe I have to write it in a, so the amortize, so using union find algorithm, union find data structure, you can do it in amortized cost of order V log star, the E log star, which means that the runtime of the Kruskal's instead of order E squared will become this plus this. Okay, so this is what union find can do. This is something that you must have seen in your books if you have read them in from the Kleinberg paradox or even the internet. Okay, I am not insisting you guys to read this thing particularly at this moment, but if you are reading it perfectly fine, I just wanted to give you an overview of what is going on here. Okay, so if you do BFS and DFS, you get order E square. If you use a slightly more cleverer, not slightly more, actually quite a lot more cleverer data structure, then you can do it in order E star n, E. And so the overall runtime goes down. And the main idea is to store this unions and unions of, store this connected components in a cleverly. And you estimate it by using the amortized time complexity. Now, the only thing that I have to kind of tell you now is what is log star n. Okay, so log star n is the number k such that, okay, so rather is the basically the minimum k such that if you apply log to n k times, then this quantity is less than 1 or less than equal to 1. Okay, so this is a very weird looking function, as you can see. And what is told is that, yeah, so this quantity is an increasing function. So as n goes to infinity, log star n technically goes to infinity. That is no doubt about that. But it is also something that it is such a slow growing function that for almost all practical n that you can think of in the world, log star n, so for all practical n, now what does practical n meaning? So the number that is like something, yeah, you can find out what is the number actually. And log star n is less than or equal to 5. Okay. And so this is a very slow moving function. So if somebody has a time complexity of order E log star E, yes, in terms of asymptotics, it is way worse than order E. But for practical purposes, this is almost as good as order E. It is almost as good as linear. Okay. Now, I mean, you guys are all coming from the mathematics background, so you can understand that this is not necessarily the smallest growing function in the world. There's no such thing. In fact, what has been proved is that for the amortized cost, so there are two results in this for union find. So there was the first result which proved that amortized cost of union find is whatever we told here, order E log E. Okay, but E is the number of such operations that you do. Okay, and it has been improved to something even better, which is called Ackermann's function. Now, I will not even try to explain what the Ackermann function is. You guys can try to read it up, but it is even slowing moving function, but again, a function that goes to infinity. So in short, the actual runtime of the union find is so worse than order E. It's worse than order E, but it is very, very close to order E. Practically, it is order E. Theoretically, it is not order E. Okay, so I think I will actually not be doing details of this amortized cost right now. Neither will I go into the details of the union find because that will really be a different problem altogether, and we have to get back to it. Maybe later on in the course, I can get back to this and we can work with it. But the union find is not the only data structure. Again, there are lots and lots of data structures that handle such kind of stuff. So you should always remember that whenever we have an algorithm and you want to do something like, how do you store something such that you want to do these following operations? In those situations, data structures is what is used. Designing data structures is a completely different ball game from designing algorithms, and there are people who can really specialize in this subject of designing data structures. And yeah, it's a really challenging area. So yeah, so here we are. So I will be happy for your assignment. I will be happy if you just explain me the correctness of Kruskal's algorithm and explain me the runtime using BFS and DFS. So it is order E square. Okay, but if you guys see at some place they are talking about union find and you want to read it, want to learn more about it, I mean, this is what the upshot of what you will be reading. Okay. Any questions on this particular stuff? How many of you have read this union find? Hello?
Yes, sir.
You guys have read, you have read the union find?
Sir, I tried to, but I couldn't understand the exact implementation.
Okay. What about others? For some reason, I'm feeling that today the class is very sleepy. Is it because of the break? How many of you are sleeping right now? Hello?
Sir, actually, I think many of us has read the union find but could not understand, so they are not replying like me.
Oh, yeah, don't be ashamed, okay? Just say it. I mean, this is a virtual class, so it's very hard to understand what's going on. So just, I mean, if you say that I have read it and I could not understand, or somebody says I have not yet read it, either of them is perfectly fine. Okay, because again, I'm saying that I'm not, I mean, insisting on you guys to read this one, but if you read it, this is what is it. Okay. So by the way, maybe I think someone send a message. Yeah, that's a good idea. Okay, so by the way, let me go to this another problem that I wanted to talk about today, and I could have started a poll here right now, which is that how many of you have actually read, uh, how many of you have read the Dijkstra's algorithm? Okay, so let me just add this one because I really want to know this. Okay, so I'm going to launch this uh, poll. I really want you guys to be honest about your evaluation of yourself. Okay, and it is very important because see, I am not going to. Uh, I'm not going to know who has submitted what, but I really want to know uh, what is the current situation. Okay, I don't know. I mean, it's not a personal thing. Okay, somebody told that I should take a poll on how many people are sleeping. I think I got the answer. The 5 people, I think, have not yet answered. The 5 people are sleeping. Okay, I think. So I only got answers from. Chandrima, are you there?
Yeah.
Okay, so you are there, I am there. So there are only 26 people other than we two. So, okay. Okay, so what I can see is that there are quite a few people have read it and understood it. Okay, that's very good. That's very nice. Uh, Almost similar number of people, something around 8 or 9 people have read it partially but could not understand parts of it. That's also perfectly fine. But there is another 1/3 of the people, which is around 9 people, who have either barely read it or not at all. Okay. So again, I don't know who is the people who are in this group. It's a completely, uh, it's completely anonymous poll. But please pull up your socks in this virtual class. I mean, I cannot keep on doing everything for you. You guys have to do it. And if you don't read it yourself before we come for the class and all, you will struggle a lot. Okay. So first of all, there are only 26 people in the class right now, which is basically 11 less than, no, 9 less than, sorry, the 10 less than what the total class strength is, right? 10 or 9 less than what the total class strength is. And there are 9 people who have either barely read it or not at all. So that is not a very good thing. I mean, it is very much possible that you guys are not enjoying this course, but again, that is something we can have a chat on that. If you have any uh, suggestions of why you are not finding it interesting, this subject and all, we can discuss that. But not reading it is not going to help you at all. Okay, so please pull up your socks and uh, try to come prepared as much as you can for the next classes and all. By the way, the course will become, I mean, till now the course, whatever was going on was somewhat just basically creating the base. So from now on, the course will be a bit faster. Okay, and the reason I gave you the 1 week break kind of stuff is because so that you can uh, uh, catch up with this subject, read up the stuffs and all. Uh, yeah, so I don't know whether it's not a very exciting situation to know that some 9 people are not coming to the class and 9 people are not coming there prepared. So half of the course class is not uh, available. Uh, so by the way, again, in this particular aspect, I want to know. So I still have not got any response from 2 of your friends. What are those? This Tadu uh, and
So probably not Taru.
no, not Tadu, not Tadu, the other one. Tell me, this, you guys know the names.
Talking about Prabhu and Nitin.
Prabhu and Nitin, right? Correct. So, do you have any idea what's going on there? I mean,
Sir, Nitinda was attending another class. Like he was in the official statistics class. So there I asked him,
yeah.
but he just replied with a sad emoji and nothing else. After that, he had gave no reply to me.
Okay. And what about Prabhu? I mean, is he alive? Have you guys chatted with him, contacted him?
Yes, sir.
So,
But he only replied that he will talk with you.
okay. I mean, if you want, you can send them a message. I have sent a message, and I think I am going to report to the dean's office about this thing because in this particular virtual class thing, I mean, I cannot do much about it. I mean, this is not something that it's pretty complicated for me to, and uh, so yeah. I mean, I can understand they have some problems. I can understand they have some internet problems and so on, but I cannot understand that they have so much problem that they cannot neither contact us or the TAs or you guys or something by phone, by mail, by whatever things. I mean, that's just not. Yeah, so I think I'm going to report it to the dean's office because at the end of the day, as I told you, this assignment will have carry a lot of weightage. Okay. Okay. Anyways, so I don't want to spoil the class for the other people who are actually coming to the class. So good. So so the main idea here is that we want to compute the shortest path in a graph. Okay, so I have given a graph G, which is a V cross E. We can think of it as a directed graph. Okay, I mean, it doesn't matter if whether it's undirected or directed. And the main idea is that I have given a two vertex U and V, and I want to check. Oh, and right, and I have a edge weight, a weight function that is goes from E to the reals. Okay, so let's assume that we are in positive reals. Okay, I will come back to something later on about what happens in the case of negative real numbers, if there are. But let's say that we have a positive real numbers. Okay, so basically I have some graph like this. Okay, and I have a different graph soon enough, so maybe, or let me not draw this line. Sorry. Yeah, so let me just give you. So say here is a graph like this. Okay, So I have these nodes A, B, C, D, E, F, G, and there are edges, directed edges, right? And I have these numbers which represents the weight on the edges. Okay. And what is it that we want? We want to find the shortest path from U to V. What does it mean? I want U equals to say U naught, U1 till UT, which is V, such that UI plus 1, they are all directed in the correct direction, where I is basically between 0 and t minus 1. Okay, and okay, so this is a path. Okay, so this is called a path, a UV path. Let's call this one a UV path. UV path. Okay, and what I want is the weight of a UV path, of a particular UV path. So this is equals to summation of the weight of the all the edges, right? UI plus 1, I equals to 0 to t minus 1. Okay, and I want to find the minimum UV path, minimum weight UV path. Okay, so this is the problem that we have in hand. I have a graph, a weighted graph, say weighted directed graph, and I want to compute the minimum weighted path from U to V. Okay. Now, how do you compute? Let's say here is this graph, right? Now, how do you compute it? Say I want to compute the path, the shortest path from say G to say A. Okay, so I want to, so if I want to do that, so G is equals to U, this is equals to V. How will you compute it? Now, of course, note that there are a lot of paths possible, correct? In a graph of size n, how many possible paths can there be from U to V? Any guess how many paths can there be from U to V?
In the worst case, n minus 2 factorial.
Yeah, in the worst case, it can be n minus 2 factorial. In a complete graph, it can be n minus 2 factorial. Okay. Now, you have n minus 2 factorial, that's a massive number of paths, and out of which you have to find the minimum. Now, see the BFS and DFS and all of those, they hardly care about edge weights, right? They hardly care about edge weights. So they kind of, so like somewhat like a BFS, if you kind of think of it, BFS will kind of produce the shortest path in terms of the number of edges. But that need not be the cheapest, right? So that need not be the least weighted path. So for example, here if you do a BFS and DFS, so you do a, either a BFS or DFS from U, okay, you have to see that, I mean, I don't know what will happen here, but it is very much possible that it will not output the path that will output by both, either the BFS or DFS might actually be a completely bizarre looking path. no, much more heavy weighted path. Okay. The other thing that you can do is some kind of a ad hoc ways, like say, okay, in BFS, for example, you always choose you start with you look at a vertex and you look at all the neighboring edges, all the neighbors, right? And you go on along one of the path. Maybe you would like to just take the path which is the least weight. Now, that might be good in some sense, but will that always be good? That is not very clear, right? So for example, if I start from G and I say, oh, okay, what is the least weight path? Oh, it is 9. Okay, I go to 9. Oh, okay, from E, what is the least weight path is 1. I go to 1. Okay, I go to, then the least weight path is 2, but then they come back to U. Oh, so that's not useful. Maybe I can take the least weight path from C, which is 8. I come to B. But you can always already see that I have already spent more than what I should have. Because for coming to B, I should have come directly from C. I mean, this is a 1 plus 8, which is 9 length 9, whereas the direct thing would have been 9, would have been 7 only, right? So this is not good. So in fact, all this kind of ad hoc ways of breaking ties in some sense, in the case of DFS and PFS, would not yield you anything. Okay. But think of it, what is it, how would you solve the problem? How would you solve this problem if you were asked to solve it yourself? The solution is kind of very interesting. Okay. Solution is not to find the shortest path from U to V, but to find the path from U to everywhere else. Okay, it's a single source shortest path. It is sometimes called the SSSP, single source shortest path. Single source shortest path. Meaning, you want to compute the smallest path from U to V. That is hard because you never know. Maybe you have a particular vertex that is completely out of the way. Okay, and somehow by going through that path, that vertex, you might have been the minimum. Okay, so in that case, you would have to touch every vertex, right? And another important knowledge is that, say I have a path, okay? Say, say that this path is the shortest path. I mean, just say that this is the shortest path from U to V. Or maybe this is not the shortest path in any case. So let's say that this is the shortest path from the U to V. Do you see some interesting thing here? This is the shortest path from U to V, but it also means that if you go along this path, it is the shortest path from U to this vertex. It is also the shortest path from U to this vertex. So in other words, if there is the shortest path from U to V, then you take any vertex in the middle. This must be shortest path from U to W also. Because if there was a shorter path, say if I have a shorter path here from U to W, then I could have gone along this shorter path and then gone over this path, and I would have created a even shorter path from U to V. So if I find the shortest path from U to V, I better find the shortest path from U to W, all of which are staying in the along the path from U to V. Right? Any questions? I mean, these are like very simple observations that we are doing, kind of obvious observations. But this is where it becomes interesting. So this basically means that if you have to convince me that you are in a shortest path from U to W, U to V, you have to convince me that you know the shortest path from U to W. And not only that, maybe there is a part thing Z over here. You also have to convince me that this is the shortest path from U to Z, because from Z there is a direct path from V. Unless you convince me that see the shortest path from U to Z is more than something, how will you convince me that that U to V through Z is not a shorter path? So in short, the best way of convincing the shortest path from U to V is to compute the shortest path from U to everywhere else. Okay, good. Now with this, we want to do something. So I start from this G. At this point, what do I know? At this point, I know that G is the, okay, I start with G. So that means the distance from G to G is, of course, 0. So this is a 0. So this is 0. Right? This is no problem. Now, forget V. Forget, I am not, see, now no longer V exists, because if I am trying to find out the shortest path from U to everything else, right? What is it that I want? I just want to care about U. I don't have V at all in the picture. Okay. Now, do I know the shortest path from G to F? Is G to F the shortest path being? So maybe I will add an edge, okay, just to kind of make life slightly interesting. So let me add an edge over here of size 1. Do you think that the shortest path from G to F is 11?
No, it is 10.
It is 10, right? But think of it yourself. You are right now standing at G. You have no other knowledge about anything else. Okay? You have to make the first move. Right? How will you make the first move? First move is that among them, can I find out anything? So I am just saying F is a distance 11 from G. G is a distance, E is a distance 9 from G, and C is a distance is infinity at this point. So I can say that E is a distance 9 from G, and this is the shortest. I want to say that. Why? The reason is that this 9 is less than 11. So at this point, say there is this U and there, or rather G rather, right? And I had these two things, E and F. E was 9, G was 11, right? So maybe there are some more, okay? In general, there can be some more. But out of them, this is the shortest or smallest edge going out of G. Smallest edge. Okay, I claim that the shortest path from G to E must be this quantity. Why? Because if I have some other path, so it is not, let's say without loss of generality, it is not. So that means I must go out of G through some other point, right? Say here, I make a move and come back here. Maybe this is the shortest path from G to G to E. Can it be? Can this? Huh?
No, sir.
Why not?
Because weight of every other edge emanating from G is more than that from G to E.
Right, because I have assumed. Okay, now here is a very important thing. I have assumed that all the edge weights are positive.
Positive.
So that means the weight of this path must be at least the weight of this edge, which is 10. Right? So that means the edge weight from G to the path, the shortest path from G to E must be more than or equal to 10. But I have given you a path which is less than or equal to E. So at this point, I cannot say what is the shortest path from G to F, but I can say the shortest path from G to E must be 9. This much we can say. Okay. Now also note that why can't we say from the shortest path from G to F is not 11? The reason is that there might be a path like this, and that path might be much smaller, right? So it is crucial. So in that case, I cannot say that this path from G to F, I mean, this path is bigger than 11. All I can say, this path is bigger than 9, but that together it might be less than 11. Correct? Fine? So,
Yes, sir.
so at this point, therefore, I know that I can write this one. G is a distance 0 from itself, E is a distance 9 from itself, and that's it. At this point, that's all I know. Okay, I cannot. So I have used two crucial factors here, that I am choosing the edge that is going out, the minimum weight that is going out, and more importantly, I am using the fact that we are all positive weights. This is something I am crucially using. Note that. Okay, this is a very crucial thing that I do. Good. Any questions so far? Okay. If not, then what is the next thing that I would have done? I am at this point. Okay. Next thing, what should I do?
In the least edge, like least weighing edge, going out
I
of
take the least edge. So think about it. Okay, let me draw some graph over here. Okay, I have a big graph, inside which I have a small graph, inside which there is G, okay, or U rather. Now I know among here, I know all the shortest path from G, from the U to all of these vertices. Correct? Okay.
So what are these vertices?
Okay, so these are this vertex. So right now I am this one, right? I'm saying this is my smaller edge. Okay, I have G, I have E. So these are the vertices for which I know the shortest distance from G.
Oh, okay, yes.
Okay, I have arguably confirmed it. Okay, at this point, just one vertex is there, but it will soon increase. Okay, fine. Now, I mean, like I will change this things a bit more again. Okay, let's say that this edge, say both these edges are. So this edge is 4, and this is 3. Okay, let's say this is the case. At this point, the smallest edge going out of G is of course 11. That's not useful, possibly. But smallest edge going out of E is what?
3.
3. So should I take 3 and go and say that the edge, should I use 3 and go and say that, oh, so this, the best way of going from G to F is through E and then there, sorry, and then through this E?
Rather than assigning this edge weight 3, we can assign it 3 plus 9.
I can assign 3 plus, edge weight is 3. What should I,
Rather than sorting directly via edge weight,
yeah,
we sort via 3 plus whatever the cost of E was.
whatever the cost of
Reaching E
was. Good. So the main issue is not the edge weight, but in other words, you can say that the main issue is what is the currently the distance from a particular vertex to G. Okay, so maybe let me do it in a slightly different way. Say, so let me start from all over again. You will see what I mean here. Okay. So let's say that to start with, what all do I know? I know that edge weight of G is 0. Okay, that I know. But the edge weight of everything else. Okay. So, oh, let me not do that one also. Sorry. So let's start with that edge weight of everything. Let's start with infinity. At this point, I don't know of any path from anywhere to anywhere. This is my starting point. Then G comes. So it's a very greedy thing that we'll do. Okay. So when G comes, I said, oh, see, G has come. So that means I know that the edge weight of G, since G has been selected, at this point G is selected, and at this point G therefore has weight 0. Now once a vertex has been selected, all its neighbors will be active. Okay, so the neighbors are, what are the neighbors here? Our neighbors are F, E, and that's it. F and E will shout out, say that, oh, see, now you know that the G is selected. At this point, till now you are saying that to reach me, the total cost was infinity. But now I know that to reach G, it is 0. So if you can reach G in 0 step, you can reach me by at most 0 plus 11, right? So 11 steps. So that means I can therefore update F as 11 and E gets updated to what? G plus 9, which is 0 plus 9, which is 9. Yeah, got it. Now, at this point, I choose so I know that at this point, I can read G in 0. G is marked, okay? So let me mark G over here. So maybe this is not a very good marking that I can do. Okay, so I can mark G. A marked G meaning that this G has been formally decided that this is the minimum distance from G. Okay, this is the shortest distance I have calculated. At this point, I take the shortest, the smallest of all these edges, which are A, B, C, D, E, F. Which is the smallest? It is E. So, oh, good. So at this point, I will therefore mark E and formally say that this path from E is the shortest distance from G. Now E gets marked. As soon as E gets marked, all its neighbors are saying that, see, you have been updated. Your cost has been updated. Right? Then our thing should also be updated. Who are the other ones? So the neighbors are here C, B, D, and F. Right? So what does C say? C says, see, right now there was no path from going from G to C. But now that I know that there is a path of length 9 to go to E, and there is a direct edge from E to C of length 4, so that means I should be updated. So there must be a path of length 9 plus 4, right, to C. So C gets updated to 13. What about B? B also has the same thing. B now, till now there was no path directly from G. But now there is a path from G to E of length 9. And since I know that there is a path of length, an edge of length 7, so I can now produce a length of path 16, 9 plus 7, which is 16 to B. Similarly for D, D becomes 14. What about F? So F, there was a path of length 11, right? Now that there is a path of length 9, okay, so F says that, so therefore through E, there is a path of length 9 plus 3, 12. Should I update F right now? Hello?
Yes, sir.
I think we should check the minimum.
Yeah, we should not update it.
We should not update. The idea is that every vertex tries to, in a distributed way, maintain the minimum path length from G to itself. Okay, as I know, as they know. Okay, so at this point, the minimum path length from F to G is 11, but if you go through E, it becomes 12. So that is not useful because that's the higher cost thing. So I don't update. Now what? Now here is the next step that I want to do. I want to see that, okay, let's look at all these A to F, other than the ones that have already been marked, okay? In this case, look at the minimum. Minimum is F. And I say that I can now mark F as saying that this path, so F, I know that the minimum distance from F to G is 11. And of course, that is coming from this path. Question is that why am I correct? So this, we are correct because, so if this is the whole graph, and this is a shorter graph. The shorter graph is basically the set of 8 vertices that has been marked red. So these are the things for which I know the shortest distance from G to all of them. Okay, I know it. Okay, and at this point, every other things outside, okay, they have a particular smaller path, right? Note that these paths are all connected to some edge or not in the red edges. Okay. Now you found that this weight is minimum. Then why is this path? Now I have to find some path. Why is this path the minimum from this G to the blue edge here, blue vertex? Say if not, okay, let's do the same thing. If not, so then that means there is a path from here that goes to this blue path through some other places, right? Whatever it is, it must cross this boundary at some place. So there is a path like this. It must cross this boundary, right? That means it must pass through some particular vertex here, maybe itself directly. So this is a shorter path from G to this thing. Can that be possible? If so, consider the vertex over here that is right after you have crossed this red edge, this red boundary. If the blue path, sorry, the pink path, if this pink path, this dotted path is the shortest path from this vertex to this vertex, that means this must be the shortest path from this vertex to this vertex also, right? That is what we observed earlier. So in that case, this vertex by now must have updated itself to something else. And so the cost of this vertex to here must therefore be lower than the cost of this vertex to here. But that is against the assumption that this one was the smallest path between them. Is this clear or is it not clear? Should I explain it again in a slightly bigger way or something?
No, it's clear, I think.
It's clear? Okay. Anybody has some other problems or something? So if there's no other problem, so then you can see what is there we are doing, right? At any point of time, the red circled vertices are the ones for which we have completely convinced ourselves that the shortest path is this. And at every point of time, once every round, one new vertex is colored red. And once that is colored red, all the other vertices, their weights are updated. For example, once I have taken G, right? F, then I want to update all the neighbors. So what are the neighbors of G? Of course, the neighbor of G is E, but E is already been taken care of. I don't care about it. And the other one is D. Now D, if it gets updated, it would be 6 plus 11 from here, which is 17. But 17 is bigger than 14. So I don't want to update it. So I leave it here, and now I take the minimum over those 4, A, B, C, D. Right? Just 1 second, I have to get my charger of my phone, laptop. Hello? Hello?
Yes, sir.
Yeah. Yeah, sorry, my laptop had already almost on. Okay. So now you can keep on updating this one, and now in this 4 things, which is the minimum one, it is now C. No, yeah, C. Right? So C therefore gets updated. And you basically color C to be pink, and you realize that C basically is the minimum through this edge, right? And once you have this C, the C edge is 13, and what all things do you update? Once again, you update D, B, right? Okay, there's G, G is not, has already been marked out. What about B? B is 8 plus 13 is 21. Again, that's way too much more than 16. I don't care about it. So once that is done, you look at the other three, and what you realize the next minimum is 14, which is D. Okay? And you can mark that 14. And you realize that 14 is coming from here, right? And once you mark 14, at that time, the 14th neighbors contains A, right? So you update it to, A gets updated to 14 plus 5, which is 19. And this is how basically you continue and do it. Okay.
Sir, how are we keeping
Track of the path.
yeah.
Yeah, so tell me, how will you are keeping the track of the path?
No, because we are just we are circling it, so we know ki, okay, so from G to let's say D, the path, shortest path length will have a weight of total weight, sum of the weights as 14.
Yeah, but you don't know the path exactly. The way in which I have described it, you don't know the path exactly. But you can change it slightly, right? Whenever you update it, say you update D. When you update D, you find out that see D is now 14. Okay, so consider the time when you update something. Let's like at this point I've updated A, right? When you update A, you not only store this value 19, but also in a separate array, store the vertex from which you came. Okay. You see it?
Yes, sir.
So so now for D, when D was updated, D would have stored the vertex E from which it came. When E was updated to start with, it would have updated this thing that has come. So by kind of going backward, you will be able to find out the path. Okay, so this is just a bookkeeping. Okay, so technically, this is something that you should be able to, you think of it, you will get there. So, but just
So we have to make a kind of stack for each of the vertices.
not a stack, right? You just have to take, okay, you mean to, I mean, if you say that what is the shortest path, you have to, now what will you do? The shortest path from D, say, the shortest path from A. How do I get the shortest path from A? Oh, shortest path of A is basically D, go to D. Now D is E, go to E, E is G. The shortest path from G to A is, right now, whatever is stored, is G, E, D, A. So every vertex has one value. Every vertex will store one value and one vertex. So this is the vertex from because of which it was updated last. Okay, is this clear? So for example, say if I have to change this one a bit. So here, this one was just 1, okay? So in that case, at some point of time, B will become 16, okay? So after some point of time, so at this point when, let me erase this something. Yeah, so this was the situation, right? At this point, B is right now at 16, and that is because of E, right? So B becomes 16, so B becomes marked, okay? And I know that this age is because of this E. And at this point, I have to update A. Now, what is A now? A right now is 19, and that is because it is coming from D. And D is 14 plus 5, 19. But now if we go through B, because of B has been updated, so I should be able to update this one. The value of A becomes 1 plus 16, which is 17. Oh, so in that case, I should update the A's value. A's value gets updated to 17, and I update the A's. A now no longer will be taking the coming, be reaching through D, but instead be reaching through B. So, okay, so this is something that I have, that, I mean, every vertex stores the cost of the path from itself to G, and also stores the previous vertex. That's all in the path. Okay. The other thing that you should realize is that, okay, this is something that you guys go and think and convince yourself that finally what you will get is actually a tree. The set of edges that I have marked red, that will basically produce a tree. Okay, which will basically be the G to all the nodes will be the shortest path, will be the shortest path tree. It's not the minimum spanning tree, but it's the shortest path tree. Is this clear? Whatever has been kind of explained. Now,
Yes.
yeah. So formally, there is a proof. Okay, please go and read the Kleinberg-Tardos. Okay, you will see the formal proof, how to write the formal proof, the correctness of this formal proof. Again, this is a very greedy algorithm, right? So you have to kind of convince us that exactly whatever I wrote here, right, in this kind of explanation, that why am I, whatever actions that I'm doing, why is it actually the shortest path that is being stored? I'm claiming certain things, and that has to be proved. So this is an example where a proof is actually important, just like the Kruskal's. Okay, it is not a intuitively clear algorithm because it's a kind of a greedy algorithm. We are greedily progressing. Okay, so this is one thing that is the important thing that is there. Now, yeah. So, okay. So what is the runtime of this algorithm? Okay, I leave it to you. Go and find out what is the runtime of the algorithm. Okay. So one thing you should know is that the runtime better be order E, right? It better be order E. I mean, not runtime, but it cannot be less than order E, or not even less than order. Yeah, because you have to look at all the edges to some level, right? You have to kind of look at all the edges, and so you expect it to be order E in the worst case. But since at every vertex you are updating a lot of things, right? At every time, how many times you update? And not only do you update, you have to find out the minimum over the rest of the vertices. So you will become that order V times E, or basically it is order VQ, will become the runtime of the Dijkstra's algorithm. So this is a very beautiful algorithm by Dijkstra. Dijkstra was a Dutch mathematician who came up with this nice algorithm in the early 60s, actually, or 70s, I think. It is used a lot nowadays. So now, so I have all these things.
Yes.
Yeah, go ahead.
Why is order of EV is equal to order of VQ? Are we taking E is equal to E to be order of E square?
Yeah,
V square.
E is order E square. Actually, you don't need order E. Sorry, you need order V square. Yeah, we don't need order V. I made a mistake there. Yeah. So this one is not order E. because you need to just look at all the vertices. Yeah, so it's order v square. Because you go over all the vertices. So let's see. Every time you update at most the degree number of those things, right? And every time you find out the minimum over all the vertices, so order v, right? So every round you find the minimum, which is order v, and you do it v times, so it's order v square. Yeah, but in general, E is always considered to be order v squared in the worst case, right? So we think of it E to be equal to v square. So there is a pseudocode over here. I don't you can read the stuff over there, and good. So this is the single shortest path. Now there are other things that you can do. So the worst case runtime that I told you is order v squared, but it turns out again there is some nice data structures through which you can do a lot of improvement. And you can get it down to something like this, order E plus V log V. Now this quantity is, in the worst case, it is order V square. But on special cases, when E is much lower than V square, this can be better. But this is something called using a Fibonacci heap that I am not going to talk about at all in this course. Again, this is a very nice data structures. Okay. But what I want you guys to think about is, yeah. So we had used this Dijkstra's algorithm for finding shortest path algorithm in this graph. All those things are fine. The algorithm's running time was v squared, and possibly with some cleverer usage, you can get it down to v plus E plus v log v. Very good. But there was one crucial assumption. Can you guys say what was the crucial assumption?
Positive weights.
Positive weights. How to take care of negative weights? How to take care of negative weights? I want you guys to think about it. Is this problem well defined? To find the minimum distance between u and v when you have negative weights. Is it always well defined or not well defined for some places? Or the cases where it is well defined, how do you find it? Okay. So I want you guys to think about it and try to come up with some algorithm on that in that way. Okay. So I think in the assignment, in the next assignment possibly, we will be giving you one problem where you would basically solve it for yourself, how to handle the negative weight cases. Yeah, go ahead. Somebody was saying something.
Sir, can't we add the minimum weight to all of them to make all positive?
Can you do that? Think about it. Think about it, what will happen? Will it always give the correct answer? Yeah, very good suggestion, but is it correct? Is that correct? So Chandrima, can you take a note of this particular problem, that how to take care of negative weights? So this is something that will be there in the next assignment. Okay, good. So let me stop here. Oh God, I have really overshoot my time. Okay, so I will stop here. So this is the Dijkstra's algorithm. So 1/3 of the people who are attending this class told that they have not read it. So please go and read it. I mean, I cannot do much about. I cannot help you guys if you don't read it. As far as I understand, this Saturday, I think we have again a holiday. This is an official holiday from the institute, so I cannot take a class on Saturday. So we will again meet on Tuesday, and we will start with some other stuff. I will let you know. I will send you a message about what is the next thing that I want you guys to read. Okay. So please come. I will just update it after this class only. And yeah, so please read it. And of course, there is this assignment that is due on next Monday, I think. Monday, right? So yeah, work on that. And yeah, also I mean, if it will be great help for you as well as me, as well as your friend, if you can somehow let me know why are the people not coming to the class. If I mean, I can see that 1/4 of the class is not coming to these lectures. I mean, if they're finding the course easy and something like that, that's perfectly fine for me. But if it is for some other reasons, then please inform me. Even if it is because they are not enjoying the class, that will be, or ask them to contact me. That will be even better. Okay. So, I mean, one of you, I mean, multiple of you, whoever is have contact with the others, they can inform their friends to contact me if they are not, if they have issues about attending the class. Okay. So if there's no other problems, let's stop today. Fine. Okay.
Sir,
Thank
Yeah.
you, sir.
Yeah. Somebody is saying something.
sir, you didn't send the slides of DFS.
I have not uploaded that in the slide in the web page. Oh, maybe I forgot. No, there are there. See class notes here. Can you see?
Oh,
Yeah. And there is also the notes of DFS that is in the PDF that I kind of linked here.
can you please send these as well?
Yeah, I will do that. Okay.